Hello everyone, and welcome to this video covering section 7.4 on finding the length of an arc and the surface of revolution. Our objectives for this video are 1, to find the length of an arc of a smooth curve, and 2, find the area of a surface of revolution. Now the one thing you're going to have to keep in mind on this is in order to do these two, we're going to go and refresh your memory on an old friend, the distance formula. But we're going to introduce, probably introduce a new one called a frustum. A frustum is what you get if you take a cone and you cut off the point. It's like the base of that cone. Okay, so that will come into play with the surface of revolution, and we'll be using the distance formula to go through and work with the arc length. Let's start out by taking a look at arc length. So in this case, f has to be a continuously differentiable function. In other words, what that means is that it has to be a smooth curve. If it's not a smooth curve, then the derivative doesn't exist at certain points. And so therefore, the whole idea of the arc length is going to kind of fall apart, as you'll see in terms of the algebraic stuff we're going to do. But it has to be continuous on that closed interval. Now, the thing you have to remember on this one is I can approximate the length of the curve by using line segments. So one thing I could do on this, if I wanted to, I could go through and just connect those first 2 points. I could find the length, and that would be an estimate of that arc length. Not a very good one, but it would be one. Okay, so what I'm going to do though instead on this is I'm going to go and I'm going to partition my interval. So you already see I have the x1, x2, and x3 there. I'm just partitioning it. It's not necessarily a regular partition in this case where all the delta x's are the same, but it is a partition that we have. And so what I can do with that then is I can go through and I can evaluate the function at each one of these different points, and then I can go and connect those points there and there, and I can add up those lengths to go and give me an approximation. Now the one thing I'd want you to recognize on this is that the more intervals that we partition this into, the better that approximation is going to be. And so what we have, we can approximate the length of each segment by just our old friend, the distance formula. And you'll recall that distance, d, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. And so what happens on this, if I go through and partition this thing and add up all of those intervals, I'm going to get an approximation for the length of our arc. Now, what we use, the notation for arc length is lowercase s. So in this case, s is just going to end up equaling the sum as I goes from 1 to n, whatever that partition happens to be, of the square root of x sub I minus x sub I minus 1, that thing squared, plus y sub I minus y sub I minus 1, that thing squared. And if I take those and add that up, this should actually be approximately equal to that. Okay. Now what I want you to do is take a second, pause the video, make sure you're comfortable with what I have done right there. Okay. Make sure you're comfortable with how this summation would work and how that would add that up. Because what we're going to do in the next frame is we're going to go and do some algebra with this on this mess here and go and get our arc length formula. Okay, welcome back. Now let's take a look at that algebra stuff I was talking about. So what we have right now, we know S is approximately equal to the sum of this. Well, this delta I, or x sub I minus x sub I minus 1 and y sub I minus y sub I minus 1, x sub I minus x sub I minus 1, that's just the change in x. So we'll call that delta x sub I. And this is just the change in y, so that's delta y sub I. So I can say that this here, that expression there, is equal to the sum as I goes from 1 to n of the square root of delta x sub I, that thing squared, plus delta y sub I, that thing squared. Now here's the trick on this one. What I'm going to do now is I'm going to pull a factor of delta x sub I squared out from this. So when I do that, I pull that factor out, what's going to be left here is the 1, but when I pull it out from here, it's going to be delta y sub I. It would actually end up being the delta y sub I squared over delta x sub I squared. But that right there will simplify by exponent rules. That simplifies to this. And so when I go and pull this out, because I'm taking the square root, and so I can just go and take the square root of you have a square root of a product, so it's going to be the square root of the first times the square root of the second. So that would end up simplifying to be the sum as I goes from 1 to n of the square root of 1 plus that delta y sub I over delta x sub I, that thing squared, times delta x sub I. Now, here's the next part on this. What happens here? S, the actual length, is going to be the limit. Now, this notation right there, if you're not familiar with it, it's called the norm of the partition. The norm of the partition is the largest value of the delta x's. So when you have a regular partition, then it's just delta x is always the same. But if you don't have a regular partition, it's just a partition. They don't say regular. We can't assume that delta x is the same. Then that would mean that this is saying that as the largest change in x goes to 0, that means all the others are going to go to 0 as well. The limit as the largest change in x, the norm of our partition, goes to 0. Of the sum as I equals 1 to n of the square root of 1 plus this delta y sub I over delta x sub I, that thing squared, times delta x sub I. Well, if you think back when you're working with, when we first were dealing with this and defining integration, this right here, that norm, what that led to is that this was S was equal to, the summation became another thing that S, starts with S, that looks like an S, that sum from A to B of the square root of 1 plus, now here's the next part. Basically what's happening is delta x sub I is also going to 0. And what you have there, as this goes to 0, as this thing goes to 0, this right there, delta y sub I over delta x sub I, that should be familiar to you. That is going to become the derivative. So 1 plus, there we go, y prime of x, that quantity squared, and delta x sub I becomes dx. And so that leads us to our formula for arc length. And then we can go and formalize it here. In this case, when we're going to let y equal f of x, represents a smooth curve on where x goes from a to b. The length of f of x between x equals a and x equals b is this integral, which we've just seen. We saw how that came about. But now keep in mind that we could be dealing with things that are a function where x is written as a function of y. And so in this case, we're going to let x equal g of y represent that smooth curve on an interval where y goes from c to d. And the length of g of y between y equals c and y equals d is equal to this, the integral from c to d of the square root of 1 plus g prime of y, that thing squared, dy. Now let's take a look at an example. Okay, now on this example, you can see I've already have it written out here. Okay, so in this case, what we're looking at is our equation is in black. The original problem's in black. Example is y is equal to x to the fourth over 8 plus 4 plus 1 over 4x squared on the interval from 1 to 3. Now I wanted to do this one here because the algebra in this one is a little bit more complicated. So I am going to ask you to go a couple times to pause to make sure you're comfortable with what I did. And then we'll move on. So the first thing I did with this one is I recognized, the squared here. That's going to be the same thing as 1/4 times x to the negative 2 power. If I pull that x squared out of the denominator. So y is x to the fourth over 8 plus 1/4 x to the negative 2. Now I did that because I know I'm trying to find arc length and I need to find y prime. And it's easier to take the derivative of this thing just using the power rule than it is to go and keep that x squared in the denominator and try to work with it from there. And so what I get there when I take the derivative is y prime is going to be, that'll be 4x cubed over 8, which would be x cubed over 2. And then this will be 1/4 times negative 2x to the negative 3, which will become negative 1/2 x to the negative 3. Or I get x cubed over 2 minus 1 over 2x cubed. So I have that one, okay? Now the next thing I have to remember is, in the arc length formula, I need that thing squared. I need y prime squared. So what I'm going to do now is I'm going to go and I'm going to take my derivative and I'm just going to basically go and square it. So remember, it's going to, when I do that, when I take that and square it, it's going to be x cubed over 2 minus 1 over 2x cubed times x cubed over 2 minus 1 over 2x cubed, and I'll have to FOIL that out. And when I FOIL it out, I will get x cubed over 2, that thing squared. I am not going to multiply it out. I'm going to keep it like that. Minus 1/4 minus another 1/4 plus 1 over 4x cubed, or 1 over 2x cubed, that thing squared. So right now I'd like you to go, pause the video, make sure you're comfortable with this and how we got to this point. Okay, welcome back, and hopefully you're all set. If you're not sure, make sure you go through and ask in class. So in this case here, when I go and combine the 2 1/4, that'll get me x cubed over 2, that thing squared, minus 1/2 plus 1 over 2x cubed, that thing squared. So now I'm going to set this thing up into the arc length formula. So in this case, lowercase s, arc length is the integral from 1 to 3 of the square root of 1 plus this thing here, there, that y prime squared, which y prime squared was equal to this. So I have that. Now what I'm going to do is I'm going to combine the like terms. And when I combine the like terms, the only like terms I have are the 1 and the negative 1/2. So when I combine the like terms, that's equal to this. And at this point, this is where I want you to go through and I want you to think about what you're seeing. Because if you look at that and you look at that, you'll notice that it's basically the same thing except for a change in sign there. Okay. You can also go through on this one. You could pull out a common factor, and then it would be something you could go and simplify from there too. But I tend to go at this and just say, look at this thing right there, that is equal to x cubed over 2 plus 1 over 2x cubed, that thing squared. And when I simplify the square root, this now, my arc length is now s equals the integral from 1 to 3 of x cubed over 2 plus 1 over 2x cubed dx. And when I integrate that, that's x to the fourth over 8 minus 1 over 4x squared, going from 1 to 3. And I evaluate that, and I get 92 over 9 as my answer. So what I'd like you to do at this point, I'd like you again, pause the video. I want you to make yourself comfortable that this here equals that. Okay? You can do that by trying to look at this thing the same way as a binomial squared. If you can recognize that. If you can't, then what I want you to do, square this, square that, pull out the common factor, and try to go and factor it from there. Okay? See which one works best. But you want to go through and get that from this point here, that this is equal to that. Okay, pause the video, and after you're done with that, we'll move on. Now we're going to go through and look at the area of a surface of revolution. So what's going to happen here is I'm going to take a smooth curve and I'm going to rotate it around in this case, I'll just do the x-axis, and I'm going to create a solid. Okay, and I want a surface, and so in this case, I'm not looking at the volume. We're not looking at the volumes like we did with the disc, washer, and shells in that case. We're looking here at just taking our curve, that portion, and rotating it around the x-axis. And what we do is to approximate that when we do it. If you're looking in the book, or you go into the 7.4 into WebAssign and take a look at the book there, you can see some good drawings. My drawings are not going to be that great. But what we can do to approximate that is, again, we can go through and approximate this by going through and connecting 2 points on the curve. So in this case, I'm just going to go with the one here that connects the points at A and B. And if I go through on that, I've tried to go through and put some points here. Let's pretend that I got these right. And so if I was to rotate that around the x-axis, I'm going to get this. That's a frustum. Okay, it's frustum. And that frustum has a surface area, lateral surface area. Now that lateral surface area is equal to pi times s, lowercase s, times r plus capital R times capital R plus little r. Now that s, that lowercase s, represents arc length. We've just seen that. Pi is the normal. Now r, capital R and little r. Capital R is one of the radii of the frustum, and little r is the radii at the other end. Now here's the other part about this. Remember what happens on this thing, that we're going to we're partitioning this. Now I just did the one interval from A to B. But I could partition it, and then I could go and generate more frustums, and I could then add those up, and the more I have, the better approximation to that surface area I'm going to have. But one of the things that happens is as this goes through, as our delta x, remember that norm of that partition goes to 0, then these two values of r are just going to end up being the same thing. And so ultimately what's going to happen is that this lateral surface area here is going to become 2 pi times s times the radius times R1. We'll call it R1. This R1 is different from those. Okay? That ultimately is what's going to happen. And so arc length, we already know what that is. And the radius, that R1, that is going to represent, R1 equals the distance from the curve to the axis of rotation. Now, generally, when we're working on these things, our axis of rotation is going to be either a horizontal line or vertical line. Okay, so based on that, that can change what that radius is going to be. Okay, let's take a look at this definition. So now again, we can go through and we're going to define these. Okay, and in this case, we're going to let f of x have a continuous derivative on the interval from A to B, and the area S, capital S now, of the surface of revolution is capital S equals 2 pi times the integral from A to B of r of x, that radius function, times the square root of 1 plus the f prime of x, that thing squared dx. And that shouldn't be any surprise to you, because we know that in terms of this thing, when we're working on these things with the frustum, we dealt with that, the s, that arc length. Okay, so that's where that's coming from. And r of x happens to be the distance from the graph of f and the axis of rotation. So if we are just looking at going around the x-axis or y-axis, if in this case we're going around the x-axis, then that r of x would actually be whatever our function would be, f of x. If we're going around the y-axis, then r of x in that case is just equal to x. Now, if we're working with g of y, x equals g of y on an interval from c to d, then this right here would be our arc length, or our surface area. And again, the same thing, r of y is going to be the distance from the graph of g to that axis of rotation. Okay, let's take a look at an example problem. So in this problem here, I just took a simple example on this one. Y is going to be 1/3 x cubed on the interval from 0 to 3, and we're going to take this about the x-axis. So the first thing I did is I gave a rough graph of this function, and we're going to take this thing around the x-axis. And so when I do that, in this case, we're going to end up with something that comes like this, and that's going to go down. And so we'll get this circular thing. Let's pretend I could draw something that looks decent. It is a problem that's in the book. This is problem 37 from the textbook, so you can go through from there as well. And so when I set this one up, in this case, since I'm going around the x-axis, the distance from my axis of rotation to my curve is the value of the function. So in this case, that arc length, capital S, or surface area, capital S, is equal to 2 pi times the integral from 0 to 3 of my radius, which is 1/3 x cubed in this case, because it is going the distance from the axis of rotation, the x-axis, to the curve, times the square root of 1 plus f prime, y prime. Y prime in this case is just going to be x squared, so it's going to be 1 plus x squared, that thing squared. And so I pulled the 1/3 on the outside and simplify it. This is now equal to 2 pi over 3 times the integral from 0 to 3 of x cubed times the square root of 1 plus x to the 4th dx. So what I'd like you to do right now, pause the video, and I'd like you to go through and calculate this definite integral. Do the integration and calculate it, give me an exact answer. Welcome back. I came up with pi over 9 times the quantity of 82 to the 3/8 power minus 1. Definitely not the prettiest of answers, but that's what I came up with. Now, I did this one by doing a substitution. I actually did a complete change of variable in the problem. So you'll notice here that I let u equal 1 plus x to the 4th. du is 4x cubed. So I put the 1/4 and the 4 to get it set up. And you'll notice then I did change the limits of integration as well. So when x is 0, I know u is going to be 1. And when x is 3, I put 3 there. 3 to the 4th is 81, so u will be 82. So this whole thing here just became pi over 6 times the integral from 1 to 82 of u to the 1/2 power. Did the integration and simplify and got that answer. So hopefully you got that. If you didn't, take a look back at your work. See if you can identify what mistake you made. If it helps to take this and just do this and then go back to x's, that's fine as well. It is up to you. But take a look, see if you can identify what mistake you made. If you can't, be sure to ask about it, and we'll see you in our next class.